The second phase is the evaluation phase. Okay. So the timing performance of a domino logic circuit is is what is the logic effort. Okay, so for that particular timing performance analysis, we use this logical effort. Is that clear? So what do you do inside that is there are two types of efforts, logical efforts there. Okay, one is called as the static logical effort, and the other one is called as dynamic logic effort. Okay, example is given here. We take a NOR gate. Okay, so the expression for NOR gate, all of you know, it is given as A plus B the whole bar, right? That's the basic expression of a NOR gate logic. So A plus B the whole bar is given as the complement form, right? So this is the basic thing. Now look at this. We have the value of the width of the transistor given here. For PMOS, it is 4 lambda. Okay, and for NMOS, so for PMOS it is 16 lambda, and for NMOS it is 4 lambda. Okay, this is static case. In dynamic case, for dynamic logic effort, you have 8 lambda and 4 lambda and 8 lambda. Both are 8 lambda. But you see, there is an extra inverter circuit employed. Right? So this is the dynamic effect. Okay. So this is how they are categorized with respect to logical. Now we are going to evaluate. How do we evaluate? That's what we are going to see. Now, considering the inverter size of 8 lambda for the pull-up. Okay. What is a pull-up transistor? We'll ask Mr. Roshan, what do you mean by pull-up transistor? And what is pull-down transistor? Roshan?
Sir?
What do you mean by pull-up and pull-down transistor?
Yeah.
Long back you studied, huh?
Just a second, so let me refer.
We have two type of transistors, right? One is the pull-up transistor device network. That was the first thing we learned in the CMOS architecture.
Yeah, the transistor turns on to pull up the output to a
Which transistor is called
load.
pull-up? I'll make it simple. Which transistor is called pull-up?
Uh,
PMOS or NMOS? Option
PMOS,
is
sir.
PMOS is pull-up. Good. NMOS is
Pull down.
okay. Now it is given here. You have a pull-up transistor with the sizing of 8 lambda and pull down with a size transistor of 4 lambda. Okay, now you have to find out what is the logical effort for a NOR gate. They might ask you what is the logical effort of a NOR gate. So how do you do that is NOR gate inputs. Okay, the NOR gate inputs are totally taken as 16 lambda plus 4 lambda. Okay, now this is the NOR gate input. You see the transistor sizing for the NOR gate is 16 lambda and 4 lambda respectively. Okay, that is the total transistor sizing. So the total number of inputs is given as 16 plus 4 lambda. Okay, that is coming around 20 lambda. And the inverter capacitor divided by the inverter capacitance. Inverter capacitance, it is 8 lambda. Okay, 8 lambda and 4 lambda. Yeah, so the total that is given in the problem. Okay, that's what is given in the problem. Now you need to find out what is the logical effort for an OR gate. Okay, so formula is like this. So when you simplify it, it becomes 20 lambda by 12 lambda. When you simplify, the logical effort value is 5 by 4. Okay, this is how you identify or evaluate the logical effort for a NOR gate. Is that clear for everybody? I will repeat it. The logical effort is given as the number of inputs, NOR input divided by the inverter input. Inverter input is given the problem. So this is the circuit diagram given to you. From there, you evaluate what is the total input capacitance of NOR gate value, the width, the width of the transistors is added. That is the pull up and pull down. Similarly, for the inverter, the pull up and pull down is given. Okay, and you have to totally evaluate what is the logical effort. Is that clear? So this is the formula for domino logic. Okay. Now for domino logic circuit, this is the domino logic. This is for static case. This is the first case we found out, static. Now for domino logic, what would be the stuff? So domino logic, the same formula. It is the logical effort of the domino logic input capacitance divided by the total capacitance. Okay. So the domino logic circuit, the input capacitance is given as 8 lambda. Okay, connected to an NMOS device. Then what would be? So this is the domino logic. You have 8 lambda everywhere. Okay, so the total capacitance in the NOR region is only 8 lambda. Okay, but your total inverter capacitance is 8 plus 4. Input capacitance is given as, inverter capacitance is given as 8 and 4 respectively. So I add both divided by the whole thing. So when I simplify this, it becomes 8 lambda plus 4 lambda. That is going to be 8 by 12. Okay, 8 by 12. When you simplify it, obviously you end up over lambda gets cancelled over, so you end up by 2 by 3. Okay, so this is the logical effort which is required for domino logic. When you look at it, what is 5 by 4 value? 5 by 4, 5 by 3 is how much? 1 point something, right? And this is going to be 0.6. So obviously your domino logic is better. Has got better logical effort compared to the normal one. Okay. So this is what is the logical effort, and this is how you estimate. They might ask you to estimate. So that's why we just wanted to give you an idea. You should not be blank with it. Okay. Now, what is the disadvantage? In the disadvantage of or the limitations of domino, we studied about 2 limitations. One is called the charge sharing. The first limitation is the charge sharing property. And the second limitation is noise injection due to the capacitive coupling. Because of the capacitive coupling, we have got the noise which is introduced into the system. So now these 2 has to be studied. Now what is charge sharing? Okay. Now when you look at charge sharing property, I told you there are 2 places in which domino logic works. The first phase is the evaluation phase. The second phase is the pre-charge phase. Okay. When does the pre-charge phase occurs? The pre-charge phase occurs when the clock is 0 mark. Okay. And evaluation phase occurs when the clock is 1. So this is standard. We have already studied. But this charge sharing property occurs, where does it occur is when the capacitance, okay, the capacitance Cout has got a problem. Okay, what is the problem here is this charge which of the capacitance Cout is discharged in an unequal fashion. Okay, means that in the pre-charge phase, there will be the charge from VDD which gets transmitted into the CMOS or the capacitance. Okay, so that charge is stored during the pre-charge phase, right? That is the first phase. I already told you the VDD will be charging the capacitance. in the second phase, evaluation phase, the output of the charge which is showed will be discharged. Okay, this is the general working, and in that discharge phase, this V out will have a problem. Okay, so this problem is called as the charge sharing problem, which occurs in the domino logic. Okay, now how do you calculate the charge sharing? Is it is given as V equal to C out divided by Cx. Cx is the capacitance across this particular point. This C out is the output load capacitance into VDD. Okay, so this is how the charge capturing capacitor is evaluated. They might ask you, they might give you a figure with two capacitance value, and then they will ask you what is the charge tone. How do you evaluate this system? Okay, so this you should be clear when you are finding out the capacitance value, right? So this is the first thing which you should keep in mind. Now, how do you overcome? We overcome this charge sharing phenomena by making another circuit called as rails. Okay, dual rail domino logic. Okay. What they do there is they introduce a differential cascade switching circuit. Okay, they introduce a differential cascade voltage splitting, that is called as DCVS. Okay, that, or in other words, it is called as dual rails. Okay, so this phenomena of dual rails makes the domino logic to overcome the charge sharing difficulty. Okay, now what do they do there? They introduce a differential rail, means that all of you know the railway lines, right? That they create two tracks, so a differential element is created. Okay, all of you know the differential component, right? Differentiation or differential op-amp. We have done with it. So the same concept of differential rails is created uh, in the module. Just excuse me, ma. One. Sorry, ma. Official call. So we introduced the differential rail concept where you take a differential value of the two components. Okay. So the clock is given. Okay. The clock which is given at two instances, that is when clock is 0 and clock is 1. Okay, so when the clock is 0, okay, the generally the output is obviously going to be 0 because there is no operational rails created, right? Only when the clock is 1, okay, the logical output goes out to be 1. Okay, the value goes out to be 1 uh, when the structural rail is given the input. Okay, so that's how it is given, and this function f, okay, this function f, which is involved in the functional rail formation, okay, avoids the major difficulty that comes across because of the charge sharing property. That's the beauty of the dual rail domino logic subsystem. And you can also construct functions. Example, this is where you create all your functions. For example, if you want to create a NAND gate, this is where you do it. This is how you do it, right? This is okay. This is the logical element where we try to incorporate it using the logics, right? So kindly work out this thing. This is and logic, which is done over here in order to implement this dual rail domino logic function. Okay. So to sum up, what we have learned here for this section is we have done with the uh, logical effort for a domino logic gate. Okay, this is how we evaluate it. We have static and dynamic evaluation methods, and we saw the structural definition of how do they do it, and then we calculate the logical for an OR gate. Then we saw how we do it for a domino logic, how do you calculate the logical effort. Then we had two limitations. One is the charge sharing. The other one is the noise rejection part. So charge sharing is we all know that it takes place in the two phases, and the charge distribution is not proper. Because of this charge distribution not being proper, the device might get a different output, not the expected output. Okay. So this has to be negated. Otherwise, your logics will go wrong. Okay. So this charge sharing phenomena has to be made proper. So in order to do that, we evaluate the charge uh, sharing. This is the formula which is used for defining that. And then we go on to see how do you overcome that. We overcome that using differential cascade switching. So DCVS, they might ask you what is DCVS, so you should be able to expand it. That's differential cascade voltage switching system, which overcomes the disadvantage of the conventional charging system. So how do they do that? They do it using this particular functional implementation, or they use the differential dual rail system in order to overcome the domino logic differentiation. Okay, so how do they do that? They have work in two phases: evaluation and pre-charge phase, where they work it and they try to get the output. When a clock is zero, you don't have any much issues there. Inverted part, they get the required output for the valuation, right? And then any logical function, for example, AND gate, AND gate, they implement it using Rails architecture, right? So doing this, they try to overcome the chart sharing phenomena and the logical value, mainly the logical effort, whatever you're trying to do, because that's the reason you go in for this construction. When you don't get the correct output, and there is a discrimination in the output, it is very difficult, right? So we need to figure that out and clear it. For this particular method, we go in for logical evaluation of the system. Okay, I have made it as simple as possible. There are lots you can go through your textbook in detail and try to conclude the whole thing. Okay, the notes will be uploaded in your Google Classroom. You can kindly refer it and you can make your reference.